when this came about, why this came about, what the hell is dark matter?
One of the first observations to deduce the presence of dark matter was measuring the rotation curves of galaxies. So about 70 to 75% is dark energy, which is an even more mysterious idea, which we know even lesser about. And about 25% is dark matter, and a few percent is visible matter and baryons that we observe.
Wow. So visible matter includes all the galaxies, all the stars, all the gases, all the planets, all the comets. Everything is less than 5%.
Yeah. And what fraction of it is visible matter versus what fraction is dark matter? Because gravity, both visible and dark matter, have gravitational influence.
So gravitational lensing is the same with dark matter as well?
Yeah, it's the exact same. So imagine this is a big galaxy, and what you have behind is a quasar, which is very bright.
Okay.
Right? So quasar is almost a point-like object. So light from this central black hole bends around this massive galaxy. It can bend around along different paths, and so it actually forms multiple images of this background quasar.
Okay. So you see 4 or 5 or 6 images depending on how you're observing it.
That's true. Choose a field where there are new experimental results coming in, because experiment drives science forward, and choose a field that isn't very crowded, that there are not as many people working on it, because then you can make the most difference.
Okay.
So it's called quadruply lensed quasars, and these are very rare. We have probably discovered about 20, perhaps 50 such objects.
And you chose this as your thesis?
Yes.
Okay. What are exoplanets?
So exoplanets are planets outside the solar system around other stars in the galaxy.
Okay.
About 2 decades ago, we observed the first planet around another star, a star in our galaxy.
This was as recent as 2 decades ago.
Yep, just about 2 decades ago.
Wow.
And since then, there's been rapid progress, and today we know about 6,000 exoplanets.
Wow.
Maybe in the next 5 years or 10 years, we could detect something that could be a sign of life. So it's just one small blip in the spectrum, and it can tell us, it has a wealth of information.
So Arjun, just to make it simpler for the audience, we are talking about gravitational lensing here.
That's right. So gravitational lensing is this phenomena where light bends around a massive object because of the gravitational field that the object creates.
And how much space it distorts.
Exactly. So in Einstein's theory, the idea of gravitation is that a massive object distorts space-time around it, and light basically just follows a path in this distorted space-time, therefore bending around this massive object.
The curvature.
Exactly. So every particle in space has to follow the curvature of space-time, and this also applies to light. So just as planets have to go around a massive object because of the gravity, light also its path is deflected.
Okay. So this is the phenomena used. That's why it's called gravitational lensing, because it becomes a lens.
Exactly. So this also acts as a lens, and just as a lens magnifies light and focuses it, gravitational lensing, if the object that is magnifying or bending light is well aligned with the object producing the light, then it acts as a lens, sort of converging light and magnifying it.
Okay.
It almost acts like an optical lens.
Okay. So that's why it's called gravitational lensing.
That's true.
Okay. So what we're talking about is, suppose there is a huge object here.
Yeah.
And exactly in that same line of sight, you have another object.
Yeah.
So if this is a luminous object, you will not be able to see the object behind.
Yeah. So if it's exactly behind, and this object is massive enough to bend light from that object behind. So imagine this is a big galaxy, and what you have behind is a quasar, which is very bright. Right? So quasar is almost a point-like object. It's the central black hole, which is accreting, right? So light from this central black hole bends around this massive galaxy, and it can bend around along different paths. Right? There isn't just one path.
Yeah.
And so it actually forms multiple images of this background quasar.
Okay. So you see 4 or 5 or 6 images depending on how you're observing it.
That's true. So most commonly you see 2 images, sometimes you see 4 images, which is rarer, which requires more precise alignment. And so you see multiple images of the same background quasar. And this is a very spectacular but rare effect. And so these lensed quasars also help us to learn a lot about the galaxy, which is acting as a lens. And so this is a very extreme effect of gravitational lensing. But what Eddington observed to validate Einstein's theory was a much subtler effect. So what they did was during an eclipse, they went to a region which saw a total solar eclipse, and they observed a star which appears to be very close to the sun. Now, if the sun was bright and there was no eclipse, you'd not see this faint star in the background, which is very close to the sun. But when there's an eclipse, the light from the sun is blocked out, and this background star, which is almost happens to be aligned to our line of sight to the sun, light from this star is bent around by the gravitational field of the sun and is deflected very slightly. And the amount of this deflection is can be calculated using general relativity, can also be calculated using Newton's gravity. And these two results differ by a factor of 2. And so it was this effect that they went out to measure. And they saw that the star is not actually... So you can measure the position of the star when the sun isn't there.
And when the sun is...
Exactly, when the sun is there, but then when there has to be an eclipse, so that the sun's light is blocked out. And they measure the position of this star during those two different phases, and they saw that it's slightly shifting.
So, which gave credence to...
And the amount of this shift, which they first, when they calculated it, happened to match exactly Einstein's prediction, and was different from what you'd calculate using Newton's theory, and therefore validating general relativity as the more fundamental explanation of gravity.
Wow.
So, yeah, so this is an example of how, experiments validate scientific theories, even though it was just born in one person's mind. But yeah, so...
Albeit the most brilliant person that we knew of at the time.
Yes. So, going back to...
you were saying that's how you shifted on to astrophysics in college.
That's right. So, the advice that I got was to choose a field where there are new experimental results coming in, because experiment drives science forward, and choose a field that isn't very crowded, that there are not as many people working on it, because there you can make the most difference.
Okay.
And I sort of decided that theoretical physics doesn't check both these boxes. And I decided to go back to the field that I was interested in the beginning, and I decided to pursue astrophysics.
Okay, so once you decided that, what did you have to do? You said you have to take a project in your final year?
That's true. So I had to choose an advisor and pick a project to do as part of my master's thesis. And I ended up doing a project in gravitational lensing, precisely this effect that Einstein's theory predicted. And so the first part of my project was studying the theory of gravitational lensing and how gravitational lensing is a phenomenon that is explained by general relativity. So I did that, and then the project I was working on was looking at these objects called lensed quasars. As I mentioned before, if you have a very bright object,
galaxy,
and a quasar behind it, light from this quasar can be lensed, and so this is a phenomenon called strong lensing, which requires a massive lens like a galaxy, and it requires
that much mass to distort space adequately.
Yeah, and it requires very precise alignment between the galaxy and the background quasar.
Okay, you mean not just in line of sight, but the distance between them as well should match.
Yeah. So I mean they should be aligned along a line of sight. So they should appear to be right behind each other. So it requires very precise alignment.
And that's when the effect of the gravitational lensing is the maximum.
Exactly. And when it's precisely aligned, you can see 4 images of this quasar. So it's called quadruply lensed quasars. And these are very rare. We have probably discovered about 20, perhaps 50 such objects.
And you chose this as your thesis?
Yes.
Okay.
So this was a fascinating effect, and it's also useful because the positions of these objects can be predicted by general relativity if you know the mass distribution of the galaxy, right? Because mass bends space, and that decides where these images are formed.
So when you mean mass distribution, you mean what is the total mass of the galaxy?
Yeah, and what is its mass profile, how the density changes from the center of the galaxy to its outwards.
Okay.
Yeah. And how much of the galaxy is visible matter, how much is dark matter? Because
wait, we just have to come to this dark matter. It's mind-boggling, and I don't think it's very difficult to explain. But yeah, so
all this is taken into account when you say mass profiling or the mass distribution in a galaxy, not just the entire mass, but where it's concentrated, how it graduates out.
Yep. And what fraction of it is visible matter versus what fraction is dark matter. Because gravity, both visible and dark matter, have gravitational influence.
So gravitational lensing is the same with dark matter as well?
Yeah, it's the exact same. Because that also, produces gravity, bends space, and produces the same effect. And so while we can't see dark matter visibly because it doesn't produce any electromagnetic
with anything that we know of.
Yeah, doesn't produce any electromagnetic radiation. It does produce a gravitational influence, and we can measure that. And one of the ways to do that is through gravitational lensing.
Okay, so you should also calculate the amount of dark matter in the galaxy before you.
So yeah, but you need to know what the mass distribution is to predict the positions of images. But what we have is we'll see a lensed quasar, so we know where the images are. And we can work backwards and figure out the mass distribution of the galaxy and figure out how much dark matter is there. And so that's one of the...
Okay, so observationally, you can see the luminosity and come to the matter.
Yep.
And then the lensing change.
Yep.
You can estimate the dark matter.
That's exactly right. So we know how much visible matter is there because we can see the galaxy. And then the lensing tells us the total amount of matter that should be there. And therefore, we can deduce how much dark matter is there. So that's just one of the utilities of
lensing. Let's just put a hold on your project right now and delve into dark matter.
Okay.
Explain to us when this came about, why this came about, and what the hell is dark matter. I know I'm asking you a question which scientists have not answered.
Okay.
But
yes.
Help us understand this.
I think the first signs were when scientists realized that... So one of the first observations to deduce the presence of dark matter was measuring the rotation curves of galaxies.
Wait, they're using presence of dark matter?
Yeah.
That means people knew dark matter.
No. So, this was when dark matter was first hypothesized.
Okay.
Because they found it was required to explain certain observations.
Okay.
And one such observation is the rotation curves of galaxies. So,
did it come through the cosmological constant of Einstein?
Not exactly. So cosmological constant is related to dark energy, which is
not the dark matter.
Not dark matter. So dark matter is this invisible form of matter which doesn't seem to have any, or has extremely weak interaction with electromagnetism, so it doesn't produce any radiation. So we can't see it. But then it has a gravitational influence. And the way this was first discovered was when scientists measured how fast a galaxy is supposed to be rotating. You can predict that from Newtonian or Einstein's theories. And you can predict that if you know how much matter is there in the galaxy. But they realized that these rotation curves were supposed to slow down as you went further out in the galaxy because the amount of matter reduces. But they realized that the rotation curves don't slow down, but they actually flatten out at large radii in the galaxy.
So, which means, so what does that mean? That means the stars at the extreme ends of the galaxies are also relatively moving at the same speed around the center of the galaxy as compared to the ones closer to the center.
That's exactly right. So that's what they observed. So it seems like for most galaxies, their rotation curves are pretty flat. So it increases as you go from
very
the center
close to the center. Yeah.
And then in the outskirts, for most of the galaxy, it is pretty constant. And this is not what you'd expect if you just have visible matter and Newtonian dynamics. And to explain this, they realized that you had to introduce a new form of matter. So there's more matter in the galaxy than what you can see.
Okay, so what the scientists realized that this can be explained only if the galaxies were more massive.
Yes, more matter
than we thought they were.
Yep.
And that's when they said there is matter that we can't see, so that's why they called it dark matter. Is that right?
That's right.
Okay. And when did this happen?
I think this happened in the late 20th century.
Okay.
60s, 70s. One of the key people working on this was NASA scientist called Vera Rubin. Okay. And there's a new telescope launched in her name called the Vera Rubin Observatory, which just started observing about a month ago or so. So that's the connection between Vera Rubin and dark matter and the new observatory. So going back to dark matter, so this is when they discovered that there is something called dark matter. And So they eventually included this in the broader cosmological theory, and this led to a theory called the standard. It's also informally called the standard model of cosmology, or the lambda CDM theory.
Okay, standard model of cosmology or the lambda CDM.
Yes. So lambda CDM, lambda stands for the cosmological constant lambda, which is also what is used to describe dark energy, and CDM stands for cold dark matter.
Okay.
So it's a form of dark matter, which is the best theory we have so far for how the universe began and how it's expanded since the Big Bang.
Okay.
And so this theory included dark matter, and it has been very, very successful so far, and has been used to explain a lot of observations of, how galaxies are receding from us, the expansion rate of the universe, how galaxies cluster, the rotation curves of galaxies. This has explained a whole variety of phenomena.
So what you mean to say is what we had theorized and what we were observing before the introduction of the lambda CDM theory were not congruent.
Yeah, we didn't even have that many observations before dark matter was discovered of, the larger structure of the universe and so on. We didn't have a standard model of cosmology. But so once dark matter was discovered, and then eventually dark energy was discovered, so it all fit into one standard model, which is our best theory so far, but it's not perfect. And much of the effort in cosmology today is trying to push the frontiers of this theory, trying to test it and at greater and greater precisions, and trying to see if there's any deviation.
Okay.
And we can probably get into this later, but there have been some exciting results in this field also. So this is how dark matter sort of came to be.
Okay. So, I mean, when I first heard of dark matter and realized that it's about 23 to 25% of the universe, I don't know exactly how much it is. And the actual visible matter, as in the matter that interacts with anything we can observe, is only 5%.
Yeah.
I was taken aback, and I was like, what the hell is happening? So, and what most of the universe is dark energy?
Yeah. So about 70 to 75% is dark energy, which is an even more mysterious idea, which we know even lesser about.
Okay.
And about 25% is dark matter, and a few percent is visible matter in baryons that we observe.
Wow. So, visible matter includes all the galaxies, all the stars, all the gases, all the planets, all the comets,
everything,
all the asteroids. Everything is less than 5%.
Yeah, that's right.
Wow.
So perhaps one of the biggest mysteries in cosmology today is to understand what dark matter is and what dark energy is, because we have very little idea. And that's what is driving a lot of research today, a lot of the telescopes, and a lot of experiments on the ground to try and see if we can detect these dark matter particles, if they are particles at all.
Oh, yeah. I'm sorry. We've deviated enough with dark matter. I'll come back to dark energy later, but then let's complete your education.
Okay.
Nicer first.
All right.
So you took up this gravitational lensing project.
Yeah.
How did that go?
That went fairly okay. It was the first project, so progress was slow. But the problem that I worked on was so as I said, there aren't many quadruply lensed quasars that we know of. So it's a very rare phenomena. But around that time, now there are a lot of new telescopes and surveys that are being commissioned and launched. And these are expected to find many more such lenses. But the challenge is these produce, tons and tons of data, terabytes, petabytes of data.
Okay.
And they produce millions of images. And in the past, people used to manually sift through these images and try to find such lenses. But that has become more and more impractical with the large amounts of data.
Yeah.
So we worked on a project to build an automated pipeline.
Wait, this is still in college?
Yeah.
Okay.
So we built a pipeline that can which can run on its own and can identify more of these lensed quasars from large data sets.
Okay, so when you mean data sets, these are not just visual pictures, but
so we basically primarily work with images, but these are images in different bands. Okay. So they're images in different wavelengths. Mm-hmm. So you have images and you have some wavelength information as well.
Okay. So you actually built an algorithm to train, to look at the data and identify, give you positives when you had a quadruple lensed quasar.
Yep.
Wow. So you pretty much did a data science level or a data mining level exercise for your project.
Yeah, that's true. It was a lot of, working with data and data mining, as you said. I mean, it was the first project, so it's not perfect.
Okay.
The pipeline exists, but, we're still working on refining it. And I'm still working on that, but we got it to some level of completion.
So there is a lot of data science also involved in your project.
That's true.
And here I thought you were a bad-haired Einstein-looking guy sitting and dreaming about the outside world.
Yeah. So I think that's a common misconception when you talk about scientists and especially, astrophysicists. There are a lot of people who just do, sitting in an armchair and thinking sort of things. But more and more people have to, scientists have to work with data, work with observational astronomers, and incorporate data into their theories, even if they're doing theoretical stuff.
Okay.
And a lot of observational astronomy, and in fact, a lot of astronomy involves a lot of data science, because in the recent decades, astronomy has a large flood of data coming in from these multiple new observatories and instruments.
Okay.
And so people have started using new data science techniques to analyze this data, and including new techniques like machine learning and AI have found an avenue in astronomy. People are using machine learning to analyze a lot of this data. So
okay, so you did this project, and by the time, I mean, you're telling me you're still working on this.
Yeah. So I got it to some state of completion by I basically worked on this for 6 to 8 months, not very long. Because by then I had to start applying for PhDs, and then I got busy in that.
This is like a pattern repetition from your taking up the JEE.
Yeah. So another round of applications.
There you have 6 to 8 months again.
Yes.
Okay.
So then began another round of applications. So then I had to apply for PhDs, and this was a whole process, takes about 5-6 months.
Okay.
And I got busy with that. So
like you said, you were always sure that you are going to pursue this. So the logical next step is getting a PhD.
That's true. So I did think about it a little bit in my 5th year if this is what I wanted to, because PhD is a long-term commitment. So that is another 5 years where you need
at least.
Yeah, at least. And once you get into that, again, your options become narrower. From a PhD, to once you finish a PhD, you've already invested so much time in this. So you need to be sure that you want to do this.
Okay.
So
for the rest of your life, if not for a considerable period of time.
Yeah. So by then I was still very interested in this, and I felt I enjoyed the work that I was doing then.
Okay.
And I was very excited about what astronomy has in store, and astronomy is in a very exciting place right now. There are a lot of new telescopes going up, a lot of exciting new data coming in. And so that was one of the big draws for me, that, there's a lot of things happening in this field, a lot of new data, and so they'll need new people to work on this.
You almost sound like a fintech guy, see? We are capturing spending patterns. We are capturing on the data screen.
Yeah.
Wow, so it's really not that different.
Yeah. Yeah, you look for opportunities, you look for where there's new data, and you try to find a niche which has not been explored before, and
wow,
that's basically doing research. So
I mean, I have no idea about how what the process of getting a PhD is, but I would assume it starts with choosing a subject and then choosing a professor. And so how does that work? I mean, once you made up your mind that you're looking for a PhD,
yeah,
what are the avenues open to astrophysicists in India or abroad?
Right. So I think the process is different based on where you want to do your PhD. It's different in India, it's different in Europe, it's different in the US. So for example, in India, if you have to do a PhD or in like an IIT or an Indian Institute of Astrophysics or IUCAA, each of them have their own entrance criteria.
What's IUCAA for the audience?
So IUCAA is the Inter-University Center for Astronomy and Astrophysics. It's a center which is dedicated to do research in astronomy and astrophysics. It was established by some very eminent Indian astronomers, and it is basically set up It's called Inter-University Center because it's set up as a center where people from universities across India, professors and teachers can
Collaborate.
Yeah, they can collaborate with IUCA. So IUCA is the place which will have all the money and telescope facilities.
Okay.
People from universities across India can come here and use that because
Okay.
India, even now, and doesn't have a lot of facilities in universities, public universities, state universities, and so on. And so these people don't have a lot of opportunities or resources to do research.
Okay.
And so IUCA acts as that mediator who should give them opportunities, allow them to collaborate with people working at IUCA itself.
Okay.
And so this is where I did my master's thesis project as well.
Mm-hmm.
So if you want to get into one of these places to do a PhD, each of them have their own entrance criteria.
Okay.
So, and I think for most of them, you'll have to pass some kind of exam.
Okay. So they have a special exam.
Yeah. So they're
just like an entrance exam.
Yeah. So I think they do consider exams like GATE, which is used for master's programs, admissions, and IITs. Sometimes they might have the IUCA probably has their own exam, and TIFR has their own exam, for example.
Okay.
So you have to pass their exam, then there'll be an interview round. So that's the process in India. In India, they don't really look for a lot of research experience.
Okay.
It might change from place to place. Maybe if you go to some newer institutes like ICTS in Bangalore, which is the International Center for Theoretical Sciences, so there they might look for research experience. That's the process in India. If you want to apply for a PhD abroad, then research experience is very important.
Okay.
So you need to have done some research in your undergrad, and this is why the ISO system is great because you get to do research. So if you want to do a PhD in Europe, this is a more focused PhD in which you'll have to have decided your area of expertise. You pick one area and one specific problem, and you apply. So PhDs in Europe, in most places, not every place in Europe, but in most places, advertised as they advertise this as a job opening to work on a particular project.
Oh, so they advertise this as a job opening.
Yeah, it's advertised like a job to work on a particular project. So if an advisor has a project that has got grants for the project, they put this up in a portal or in the university portal saying we have openings for so many PhD students to come work on this project, but you'll be constrained to work on that particular project.
Okay, so there is no scope of deviation once you...
There is maybe sometimes, but a lot of times it's a very focused 3 to 4 year PhD where you just work on that project.
Okay.
Of course, it'll be a fairly broad area where you can do a couple of different things, but you can't completely deviate from it. And again, this also changes within Europe. So UK has its own system, which is slightly different, and Italy does things differently than Germany and so on.
Which is pretty much in keeping with the character of the European Union.
Yeah.
Everybody does something slightly different.
Yes. But in the US, the system is different. So in the US, you apply to a graduate school rather than a particular advisor or a particular research problem. So the graduate school has its own application process. You write a statement of purpose. You write a research statement. You describe what you've done through your undergrad.
Okay.
They don't expect you to know what exactly you want to work on. I think it is recommended to have a broad area of interest or a couple of areas of interest. And you can mention that in your statement. They look at your grades. They look at your letters of recommendation.
Okay.
And
it's not an entrance exam driven or a project driven, but basically an interest and acumen driven.
Exactly. So they try to look for whether you have what it takes to do research, whether you will be successful in a PhD program. So it's a very opaque process. They don't tell you what exactly they look for. Each university has its own criteria.
Okay.
And you after you submit all these materials, you either get an acceptance letter or rejection letter. They don't actually explain the process.
Okay.
But I think what everyone says is they look for ability to do research and ability to be successful in the program. So they look at your past academic record, whether you have good grades. So you need very good grades. You need to have some research experience. And nowadays, this process has gotten so competitive that even to get into a PhD program, especially in astronomy or physics, you need to already have a significant amount of research experience. You need to have published a research paper, or maybe even 2.
So you had done that along your...
So when I applied, I didn't have a publication.
Okay.
But I had good recommendation letters. I had very good grades. So I checked 2 of the boxes. And I had made some progress in the project and had gotten recommendation letters from my professors attesting to the fact that I'm working on a project. And it was an interesting project and a fairly
Of
complex one.
course.
So I think that helped me. But nevertheless, this was a super competitive process. And, you know, I applied to 20 different graduate schools in the US. And
Wow.
before that, I wanted to apply mostly in the US because of the system that they have where you don't have to pick one advisor or one research project to begin with.
Okay.
So you get into a graduate program and then you're allowed to choose between, from all the professors in the group, in the program. You can work on any project that you find interesting then. You can also switch professors and advisors, work on 2 different projects or multiple different projects during your PhD. So it offers a lot more flexibility.
It's the areas that you are allowed to explore is much more.
Exactly. So you get a lot more, breadth of knowledge and experience in the US.
That's why you decided that you want to get a PhD in the US.
Yeah. So I wasn't entirely sure of one area that I want to work on in astronomy. And I definitely wanted to explore a couple of areas. And, while gravitational lensing was interesting, I also wanted to explore something else like exoplanets. And
what are exoplanets?
Right. So exoplanets are planets outside the solar system around other stars in the galaxy.
Okay.
So just like the solar system has 9 planets that we know of, but the solar system is the only place that we have been able to observe planets directly until the last 20 years. And about 2 decades ago, we observed the first planet around another star, a star in our galaxy.
This was as recent as 2 decades ago.
Yep, just about 2 decades ago.
Wow.
So this is a very new, and since then there's been rapid progress. And today we know about 6,000 exoplanets.
Wow.
In the galaxy.
20 years.
In 20 years.
Okay.
And there have been multiple space missions, ground-based missions, and thousands of people working on this field. So it's grown exponentially since then, and it's a very exciting frontier because we still know very little about how planets form, what kind of planets exist in the galaxy, and we first expected to see planets similar to ones in our solar system when we started looking for planets, because those were the only examples we knew of, right?
Exactly.
So we knew that there was a Mercury type planet, Earth type planet, a Jupiter kind of planet, and this is what we were looking for. But to our surprise, the first kinds of planets we found were nothing like what we have seen in our solar system.
Okay, so give the audience as an example of when you say they were nothing like this thing. How exotic were they?
Yeah,
what made them exotic?
So we observed planets which were the size of Jupiter or even more massive, like tens of times the mass of Jupiter.
Okay.
So these are called super Jupiters. And these massive planets, so Jupiter orbits pretty far from the sun, right? So you've got Mercury, Venus, Earth, Mars, and then Jupiter. So it's about 5 times the distance from the sun as the Earth is.
Yeah.
Right. So, but we observed these Jupiter-like planets very close to the host star.
Okay.
Even within the orbit of Mercury. And in fact, most systems that we have observed so far,
were their host star comparable to the size of our sun?
They were a little dimmer,
okay,
but sometimes some were almost as bright.
Mm-hmm.
So these are planets that are almost touching their host star,
and
they're as big as Jupiter.
Wow.
And so one of the first questions was, how are they even able to hold on to an atmosphere? Because Jupiter is a gas giant; it's mostly gaseous. How are they able to hold on to an atmosphere when they're that close and that hot? So these were called hot Jupiters. And the Kepler Space Telescope, which is a NASA mission, launched close to a decade ago now, and which has discovered a majority of these 6,000 exoplanets, discovered a lot of these hot Jupiters.
Wow.
And in fact, the technique used to discover them preferentially allowed us to find more of these planets because there was an observational bias towards these planets.
Okay.
So
you mean the technique was biased to finding more such planets?
Yeah, that's true. So in fact,
so give us a hint about what this technique is and why is it.
So this is a fairly intuitive and easy to understand technique. It's called transits.
Okay.
So a planet is much, much smaller than a star.
Of course.
And many orders of magnitude less bright. Right. So a planet doesn't produce its own light. A star is a huge ball of gas that's burning in the sky. And these tiny specks of rock and dust basically just reflect the light from the star. So it's very hard to observe them directly, especially when the star is
Right,
the prime.
right, the star.
Yeah, and the stars themselves are points of light in our night sky.
Correct.
So the technique that was first used to find these planets was an indirect technique of looking at these planets called transits. So basically, when a planet is orbiting around the star and it passes in front of the star, if the plane of the orbit is aligned to our line of sight,
Okay.
then as the planet passes across the face of the star, it blocks out some of the light from the star.
So the luminosity of the star periodically reduces.
Exactly. So you see periodical dips in the brightness of the star. But these are extremely tiny dips because the planet is small. And so you need very precise measurements of the brightness of the star over time and very stable measurements of this to be able to measure these tiny dips in the light of the star. And by looking at how often these dips happen, how big these dips are, you can tell how big the planet is and how far it is from the star and what its orbital
And
period
can
is.
you also tell how many planets are there with this?
Exactly. So you can also detect multiple planet systems. If you see multiple dips occurring at different times, you can sort of correlate these dips to each other and say, okay, there are different planets at different radii.
Wow. Okay, so basically you're looking at a tiny speck in the night sky.
Yeah.
And you are measuring its luminosity or the brightness.
Yeah.
You're seeing how bright it is. And then when a tiny speck of dust goes around the tiny tiny spot of light that you're watching, the luminosity goes down, say, probably by 0.002% or something of that magnitude.
Yeah.
So we have telescopes that are that powerful to deduce that minute change.
Yeah. So that's why it took this long for us to discover the first planet.
Okay.
While science fiction has imagined these exotic alien worlds for, decades before that, Star Wars came out in the 60s, 70s.
60s and 70s, yeah.
Yeah. So science fiction writers have always imagined these alien worlds. And we always sort of had wondered what it would be like if there were other worlds. But 20 years ago, we actually saw the first one of these worlds.
So now I understand when you say that the technology or the observational science was biased to find these, because if there are more massive planets closer to the sun, you can see a bigger dip.
Exactly. So that is the observational bias. In fact, most systems that Kepler found are
Kepler, as in the Kepler telescope.
The Kepler telescope, not the astronomer, but the telescope named after the astronomer. Most systems that the Kepler Space Telescope found can fit inside the orbit of Mercury. So they're all very tight systems. And, the most famous one is a system called TRAPPIST, which has 4 or 5 planets all within the orbit of Mercury, well within.
Wow.
And so the star is much dimmer. And so because the star is dimmer, some of these planets actually fall in the habitable zone of this star.
Okay.
So it is possible that they harbor liquid water. And so this is a system of great interest right now because it is a multiple planet system. Not exactly like a solar system, but kind of looks similar.
Okay.
So we have found planets of different variety. We've found planets of varying sizes. We have found planets called super Earths, which are, much more massive than Earth. We have found planets called sub-Neptunes, which are, smaller than Neptune, larger than Jupiter, gas giants, ice. Well, we think they're ice giants and things like that. We have found planets where we suspect that they might have liquid oceans on their surface. In fact, we have found some planets which we think might be covered in liquid water.
Oh, wait. When you mean liquid oceans, it could be methane, it could be water,
Yeah,
it could be any...
Some of these, we have found some signs of water in the atmosphere as well.
Okay.
But yeah, none of this is, very certain.
And you do this with spectroscopy?
Yes. So the way we can probe the atmosphere of these planets through the transit method is as the planet is transiting across the face of the star, some of the starlight passes through the gaseous atmosphere. So that's as the light passes through the atmosphere, because that's not solid rock. The atmosphere is transparent. And as the light passes through the atmosphere, there are gases in this atmosphere that can absorb certain wavelengths of this light. So if you know what the spectrum of a star, how its energy across different wavelengths, so the light intensity across wavelengths should look like, and then you see its spectrum when the planet is transiting, and you see that there are some wavelengths missing, you can deduce that
it's been absorbed by the gases in the atmosphere.
In the atmosphere of the planet.
Okay.
And by this method, you can sort of build a picture of what the atmosphere should contain. And this is how we try to probe what molecules are present in the atmosphere. And this is one of the most promising methods to try and find signatures of life in the atmosphere.
Wow.
Yeah. So that's the current frontier, is to search for biosignatures in atmospheres of planets. And that is one of the uh, objectives of the James Webb Space Telescope,
Okay.
which has been launched by NASA a few years ago, which is one of the largest telescopes we've put in space, an infrared telescope. And it has the capability to look at this spectra in great detail in very high resolution and try to find different molecules. And since it's looking at this spectrum of light called the infrared, a lot of molecules, like carbon-based molecules like methane and water, have spectral signatures or observational signatures in this wavelength range.
Okay. Okay. So that is why that is why you were saying that we are looking for life signatures.
Yep.
Because it's a carbon-based
So I think,
spectrum that you are majorly observing.
yeah, so we have no idea how alien life can look like, but
Assuming it's carbon-based.
yeah, but we know how life is on Earth, and it's possible that this kind of life could have evolved somewhere else as well. And so that is the first best bet to look for, this kind of life. And the way what biosignatures are these are molecules that on Earth are only produced by life,
Okay.
and they cannot be produced in that quantity by any inorganic process.
Okay. So which means methane, the first one.
So methane can be produced by inorganic processes. It is if methane is present along with some other molecules, then we can say that there is life. So it's very rarely one particular molecule. It's usually a combination of them.
Okay.
Which
So
we're
like
considered
on a,
biosignatures.
so what are you looking for if you're looking for a sign of life? As in, what is the common prescriptions that you are looking for?
So
right now?
there isn't one prescription. There are many different combinations of molecules, and in fact, the very field of the subject of what is a biosignature is also an evolving subject. We're trying to figure out which of these are biosignatures. Can there be abiotic processes in the universe that we don't see on Earth that can produce these molecules? So one famous example that grabbed some media spotlight recently was this JWST observation of a planet where they found a signature of a gas called dimethyl disulfide, or LEMDS. So they found signs of it. It's a very weak signature, and it's highly debated that it's even there.
Okay.
But if it's present on Earth, dimethyl disulfide is only produced by bacteria in the ocean.
Okay.
So these are the only organisms can produce this in the atmosphere, and this has to be constantly produced and
It's a
destroyed.
bioorganic process to create dimethyl disulfide.
Yeah.
Okay.
So that's the process we know of on Earth, but it is possible that it might be produced in some abiotic way in the universe. So that's the whole,
So the science is not completely clear, but then there is a lot.
exactly. And, even the finding life won't be this one eureka moment where we see one planet and say, this is life. It's going to be a gradual process where, we try to rule out different things. So this group in Cambridge used the James Webb Telescope to look at the atmosphere of this one planet, which they thought was a planet that is covered by oceans, and so could have bacteria in these oceans that can produce this molecule. And as recently as about a month ago, they released a paper saying that we have found, to some significance level, some signs of this dimethyl disulfide.
Okay.
And this
Is it as
generated-
recent as a month ago?
Yeah, as 1 month ago.
Okay.
And this generated waves of excitement and interest in the community, and it grabbed a lot of media's headlines. But there is a lot of skepticism about this result. It's not,
Of course, it's a month ago.
Yeah.
People have still not been revealed
Yeah.
completely.
and because it's so sensational, the more sensational the claim is, the more solid
Need
the
evidence.
evidence. Yeah, the more solid the evidence has to be, and the evidence in this case is not solid at all. So a lot of people, there have been a lot of rebuttals to this and saying, this is not exactly life. People are saying dimethyl disulfide could be produced by inorganic abiotic processes. Some people are saying that the signature they saw isn't a signature at all. This was
Okay.
just like a random fluctuation in the data. It's not significant enough. So, it'll take a few more iterations. But the thing is, the very fact that we're able to make an observation like this means that maybe in the next 5 years or 10 years, we could detect something that could be a sign of life.
Wow. Now, I mean, I was thinking of this, and the thought just hit me and boggled me was, the distances are so great.
Mm-hmm.
Uh, there is absolutely no way we can visibly observe all this.
Mm-hmm.
But we have studied the science on Earth and near Earth sciences to such an extent that a small blip in a particular frequency or a bunch of frequencies, we can actually deduce or at least assume to deduce that there is life on another planet.
So it's just one small blip in the spectrum, and it can tell us, it has a wealth of information.
Wow. So, well, that's mind-boggling in itself.
Yeah.
Especially when you see that the visual of that particular star, which is not even the star, the visual of the star that's hosting the planet you're studying, the exoplanet you're studying, is probably a few pixels around.
Yep. So, I mean, the science of life debate will continue for a long time, but
At least the composition of that exoplanet you can study with just a one blip.
exactly. So
Wow.
that is very exciting, and that's
If that is not cutting edge science,
yeah.
I don't know what is.
So the cool thing about exoplanets now is that we have seen so many exoplanets that we're pretty certain that almost every star in the galaxy should host a planet. And
Okay.
even right now, like, which we couldn't do 20 years ago, right now, if you look up at the night sky, I can point out a dozen stars that we can see and say these stars host planets around them. And some of these planets might actually have life in them.
Wow.
So that's the cool goosebump sort of thing in the field of exoplanets.
I mean, just imagine. Well, I'm trying to picture your journey through this podcast. A first standard kid who's going to the Nehru Planetarium around the corner and then just being fascinated by the number of stars that are there.
Yeah.
Today is actually searching and wondering which one has a habitable exoplanet.
Yeah.
I
Yeah.
didn't know back then that there were exoplanets.
Exactly. Perhaps when I was first, was first exposed to astronomy in the planetarium that I talked about, we might have discovered a few planets then, and that was a field that's still growing. To today, since then, we've discovered thousands. So
Wow.
it's an exciting field to be in.
Okay, so that's how you completed your masters, and then you've applied to universities. And the reason you wanted to apply to the US was, of course, one, it gave you it was more flexible than the other places,
Mhm.
and well, of course, the kind of grants, the kind of technology, the kind of people, the amount of people working on astrophysics in the US is probably the highest.
The US is definitely a leader in astronomy and astrophysics.
And you applied for some 20 different universities.
Yeah.
How did that process go?
So
How did the selection process go?
so
As in, you're selecting what university to apply to.
right. So that was also a process in itself. So I had to narrow down university. So I tried to look for. It's also, sitting in India, it's hard to know which. You've not even heard of many of the universities in the US. You've only heard of a select few Ivy League colleges and maybe a few popular ones. So I had to talk to my advisors, people who have been to the US, who have, been through the US system, to ask, what are the good universities there which have good astronomy departments.
Okay, before all this, how many of your peers are there that you can, peers or your seniors,
Mhm.
that you can get a feedback from? Because I can understand as you keep going to towards the PhD level, that groups keep getting smaller and smaller.
That's true. So there weren't that many seniors who are doing astronomy in the US. That's a very small subset.
Okay.
I knew probably, 2 or 3 people.
Okay.
But I knew a few professors who knew students and so on. So I could talk to them. And I tried to make a list of, the best departments in the country. And it was not a complete list. I realized after going there are many more places which have really great departments,
Okay.
which is, it's hard to know sitting in India, which are which are good colleges. But the list I made were all, the most competitive, most sought after places.
Okay.
And so these were some of the hardest places to get into. So, and PhD itself is it's a more specialized field. So there are fewer positions open. And the US, once you get admitted to a PhD program, they fund you for all 5 years.
Okay.
You get paid like a stipend, which is sort of like a salary, but it isn't as much as an entry-level salary. So
That's always nice to know.
so you get paid enough to live comfortably in the US for 5 years. And because of this commitment, they have very few positions open in every department.
So because each position is pretty expensive for the university to maintain.
Exactly. So some of the most competitive places, you get hundreds of applications and then they select 10 people or 5 people.
Okay.
So
Still better odds than getting into JE.
that is true. But it's a completely different ball game. And you're competing with people who are already in the US system, who
Okay.
know how it works there and who have already trained to apply to these PhDs. Whereas in India, you don't have the same exposure. So it is difficult. And when I applied to 15 to 20 places. And I got an interview call very early on. And the very first interview call was from Ohio State. And I got admitted to Ohio State.
So the first person who called you said yes?
They said yes, more like.
Okay.
Because almost everyone else said no.
Okay.
So I got into just one place out of the 15 to 20 that I applied. And in hindsight, the place that I applied to were also very competitive. And all of them would have been selecting from roughly the same pool of students and so on. So I'm glad I got into at least one place, and I got into a great place. Ohio State is one of the best departments in the country, and it's
For astrophysics?
for astronomy.
Astronomy. Right.
Yes.
Observational part of the...
Well, astronomy and astrophysics are sort of interchangeable.
Okay.
They do a lot of they are observationally, they do a lot of observations, but they do have theoretical astronomers, astrophysicists as well.
Okay.
But yeah, so it's like a top 10 astronomy department in the US, top 20 in the world. So I'm glad they took me in.
Okay.
So I got lucky that way. But the process is extremely competitive, especially if you want to go to one of these very sought after places. I know a lot of peers who had to spend a lot more time applying. And even if your profile looks almost identical, they'll have to select between a large number of almost identical profiles. So it then goes down to very small factors.
I think people who are selecting these are pretty well versed if they can make a distinction between one gas and another again. They are pretty well versed in how to make a differentiation between exactly similar looking profiles. That probably is an easier job for them.
Yeah, probably. It's definitely a hard task, and sometimes it also is up to chance. Sometimes you need to apply to the right school that is looking for a person with your kind of background, or that has an opening in what you're interested in. And so if you're a right fit, then they take you in. And so
you get into Ohio State.
Mm-hmm.
You get accepted. And they call you and you say yes. And
so I said yes pretty early on, even before I'd gotten a lot of my other offers or other rejections. Because do
you get a rejection call, or if you don't get a call, it's rejected?
You get a letter saying with your the status of your application. But Ohio State was one of my top priorities, and there were a lot of great people there that I wanted to work with. So once they gave me their offer, they also organized like a virtual tour of the department. They gave us an opportunity to talk to graduate students, to professors. They had these sessions where professors gave short presentations about their research. So I felt it was an overall very welcoming atmosphere.
Okay.
And also a lot of great research was being done. So I accepted it pretty soon after.
And how long has it been since you've joined Ohio State?
So it's been 2 years now. I finished 2 years.
Okay, so then it's a very good time for me to ask you this question. What does it feel like to be a proper, full-on scientist into research?
So I think when you think about the big picture, it's very exciting. I mean, and even being in an astronomy department like at Ohio State is very exciting, because everyone there is doing cutting edge research in one field or the other.
Okay.
There are people using the best instruments in the world, people working on using the James Webb Space Telescope. They're using the biggest telescopes on the ground, and they're working in all different areas of astronomy. And then you get to meet all of them, talk to them, discuss, recent research papers. So it's a very...
For the audience to get an understanding and for me to amuse myself, it's like the toys you have are the Kepler telescopes, The James Webb
Yeah.
Telescope. That's the toys you play with?
That's the toys you play with. Yeah.
Wow. Okay.
Yeah. But yeah, so those are basically our instruments, and so it is a very stimulating atmosphere, and it's an exciting place to be. And when you think about the big picture, it is very exciting, the kind of research we're
You got to find life outside.
Yeah. Yeah. But I think the day to day is, it's not as exciting and as it seems when you try to explain what you're doing to someone else.
Okay.
Because most of the time you're just sitting in front of a laptop, writing some code, and you need to keep reminding yourself that the code you're writing is for this big picture goal.
Okay.
But yeah. So it's been an interesting 2 years.
Okay. So the only difference is if you were in Bangalore, you're writing code for a company who you do not know what they're writing code for. Here you're writing code for your own research.
Yes. And you can decide what kind of code you want to write, what research you want to do. So there's that academic freedom and flexibility that you get only in academia.
Oh, yeah. But I understand where you're going with this, but then a weird thought hit me. The irony is whoever Bangalore puts out is eventually coding.
Yeah, it does seem like that. Yeah.
So what are you working on? I mean, I through the podcast, I get an understanding you're still working on gravitational lensing.
I am. So I'm sort of working on gravitational lensing.
You're 2 years in your PhD program right now, which means you are a complete scientist, or you are not.
I'm
yet.
still a scientist in training.
You're a scientist in training.
Yeah.
Okay. So explain what happens in a PhD program.
So the objective of a PhD is to teach you how to do research. That's the whole objective.
Okay.
And in the US, the first 2 years of your PhD program, you do some courses, advanced courses in astronomy, so that you have a broad-based understanding of the subject.
Okay. When you mean advanced courses, these are not your masters or your thing, or are they specific courses?
They're more specialized. They might. So during my master's also, we did some advanced courses. You might repeat some of that if you do a PhD in physics. But I hadn't done a lot of astronomy courses. So these are more specialized, and we learn about specific topics in astronomy. And I had not learned about these in the past.
Okay.
If you have done a master's degree in astronomy, you might have encountered some of this.
Okay. So like what are the new subjects or the courses that you're doing that really excite you, or you hadn't heard about and you got into?
So we had courses in all branches of astrophysics. So we did a course in cosmology, and I talked about the lambda CDM model, and that's what we learned in the cosmology course. About we learned about galaxies, how galaxies form, the Big Bang. We had a course on stars, so we learned about what is a star, what is the interior structure of a star, how do stars produce energy, how do they evolve. We learned about all the physics that happens inside a star.
Okay.
And the star seems like one of the most simplest objects, but after that course I realized it's one of the most complex things out there. There's just so much physics in a star and so much complex modeling that has happened. And even today, we have known stars for the whole history of humanity, but even today we don't know completely how all the physics that happens inside a star. And there's some exciting
What
things.
don't we know? As in, even the formations of stars, is that still?
Yeah, even how stars are born,
Okay.
they're born in these nurseries, these nebulae,
Okay.
which until recently, these nebulae, they're large gases of dust and large clouds of dust and gas. And these are usually opaque to visible wavelengths.
Okay.
So most of our telescopes, which operate in visible, light, have not been able to look into these clouds.
Okay.
But with James Webb,
there is very little matter to disperse. Is that the reason?
so these clouds are very dense and they block all visible light. So they absorb and scatter visible light. But with James Webb over the past few years, because James Webb looks in the infrared, and these clouds are transparent to infrared wavelengths, which are longer wavelengths, we have been able to look into these stellar nurseries to see the first how stars are born, the first moments of a star's life, and so on. But on the physics side, there are a lot of processes that happen inside the star. Transport of energy, transport of radiation, elements inside a star, how elements are created, how they're destroyed, what elements are present.
Okay, so the elements keep getting destroyed inside the star.
Yeah. So
so let's do this. Just take us through the birth of a star from these nascent nebulae and the clouds.
So a star is born when large clouds of gas and dust begin to contract under their own gravity.
Okay.
So these have to be cool clouds so that there is no pressure pushing them outward, and they began to collapse. They began to collapse and form disks, and at the center of the disk, they collapse into a ball.
Okay.
And this ball, accretes more and more gas, becomes denser and denser, hotter and hotter, and begins to contract, and eventually reaches a temperature called the ignition temperature. So these are mostly gas. These clouds are mostly composed of hydrogen, and sometimes it has heavier elements, but in small amounts. So these hydrogen clouds, at the core of this collapsing cloud, the temperature and density gets high enough that hydrogen atoms, which are now ionized, begin to fuse.
Okay.
And when this ignition happens, this fusion reaction produces a large amount of energy, and the star basically lights up at that point.
Okay. So
And-
basically, a fusion bomb just goes off.
Yes, at the core of the star. So it's a very simplified picture. There are a lot more processes that go on. And so when the star lights up, the large amounts of light and heat it produces just blows away the rest of the dust.
Okay.
And it sort of stops the accretion of more dust. And so that's when a star is born.
Okay. So star is born when it stops growing.
Yeah, when it basically reaches ignition,
Okay.
because that's when it stops growing, because the energy pushes away the rest of the dust cloud. And in this, so as I said, the gas and dust also form a disk around the star. And it's in these disks that planets also form along with the birth of a star. And this is something which is still a field of active research. As I said, we're now peering into these dust clouds and seeing how these planets form with stars. And so as when a star is born, there's hydrogen fusing in its core. And as it goes on, it fuses hydrogen to helium. In a star like the sun, it's not massive enough to fuse helium into something heavier. So fusion stops there.
And then it becomes a white dwarf.
A white dwarf. But first, it expands into what is called a red giant.
Okay.
So when the sun does that, it'll probably engulf all the planets, including Earth, perhaps up to Jupiter.
And then it contracts into a white dwarf.
The white dwarf is
What's
the
left?
core of the star.
Okay.
The envelope just disappears
Okay.
and is evaporated away. It becomes too unstable.
Okay.
And what is left is the white dwarf. But in more massive stars, fusion continues further. Helium forms carbon forms oxygen. In fact, these heavy elements are also present in the sun because it's formed from these elements itself
But then to what
in smaller amounts. But these are not actually fusion products yet.
Okay.
But in heavier stars, carbon can form oxygen and nitrogen and so on. You go down the periodic table. But this process stops at iron.
Any reason for that?
There is a technical reason. So fusion can only happen if it's energetically favorable, right? If fusing two atoms itself requires a lot of energy to bring them close to each other to overcome the electromagnetic repulsion. And in most of these cases, when you form the fused product, that releases more energy and therefore it's stable. But because of, a quirk of nuclear physics, iron is the most stable element that you can form by fusing, these atoms together. And if you fuse two iron atoms, what you form is not as stable. So this is not energetically favorable and does not happen. And so fusing iron just consumes more energy
Than
it produces.
Okay.
So iron is sort of the death sentence for a star. And if the star forms iron, then it is so dramatic that it probably has about a day or two left in its lifetime.
Wait, a billion-year cycle comes down to a day or two?
Yep, that's it. In a few days, this iron core brings all fusion to a halt.
Okay.
And because the star is so massive, gravity collapses the star upon itself. And when this collapsing star hits the iron core, it rebounds because it hits a very solid surface. And this causes a massive explosion called the supernova explosion.
Oh.
And these supernova explosions are the brightest, most energetic things we've seen in the universe so far. When these occur, so these last for a few days.
Okay.
The whole process of the star collapsing, the time scale for that is in few hours to even minutes. So this happens really rapidly. And it's crazy because these things are on astronomical length scales.
Okay.
But this happens on very normal time scales, very quickly.
Wow. So from the birth of a star, and it has to be a supermassive star
Yeah.
for it to produce a supernova.
Yep.
Now, you're telling me that the moment the core is formed or iron is formed in the core, it's a day in the span
Yep.
of the whole star before it compresses and rebounds into a supernovae?
Yep.
Wow.
And these explosions are so energetic that they outshine the light from an entire galaxy in the few days that they shine.
Wow.
And then especially in the first few hours of the supernova going off.
How many supernovae do we see?
So we've seen a lot outside our galaxy.
Okay.
So these we've seen hundreds. Within our galaxy, we expect a supernova to go off once every century.
Okay.
The last one we saw was in the 1980s.
So we actually saw a supernova, observed a supernova in the 1980s within the Milky Way?
Perhaps a little before that.
Okay.
But it's actually been more than a century since we saw one. I think the 1981 was in Andromeda, which is close enough. But it's been a while since we've seen a supernova in the galaxy. But we expect one to go off every century. So we're sort of pending a supernova explosion, and people
Time now.
people expect it to go off anytime now. And it was so bright that, so if they happen in a distant galaxy, these things show up as these bright points of light, which are brighter than all the stars put together in our galaxy.
And they last for a couple of days.
They go down in a week or so.
Okay.
But if they happen in our galaxy, and depending on how close or far and which side of the galaxy they happen, these things can be as bright as a full moon in the night sky.
Wow. And you mean to the naked eye?
To the naked eye.
Wow.
So if a star in our galaxy goes supernovae, which can happen any day now, we'll probably see a new moon in the night sky, or at least a very bright star.
Wow.
And if it close enough, it'll also be visible in the daytime. So
Okay.
for a few days.
Wow.
Yep. So that's the end of a massive star. And depending on how massive it is, this iron core can collapse and form a ball of neutrons called a neutron star.
Okay.
And these are end products of, intermediate mass stars. But if a star is more massive than 1.4 times the mass of the sun,
Okay.
and this is called the Chandrasekhar limit. This theory of and this limit was found by Subramanian Chandrasekhar, the Indian American astronomer, who is C.V. Raman's nephew.
Yeah.
Yeah. And he won the Nobel Prize for this. So any core more massive than 1.4 times the mass of the sun won't end up as a neutron star, but collapses all the way to form a black hole.
Wow. So the Chandrasekhar limit actually decides the condition for a black hole to be formed.
Mhm.
And how many stars of such mass or size, which is 1.4 times or more than our sun, are in our galaxy?
Great. That was slightly inaccurate. So a star more massive than the Chandrasekhar limit cannot form a white dwarf, but it does form a neutron star.
Okay.
But the neutron star limit is a little more than 1.4 solar masses.
Okay.
It's about, we don't know what the exact limit is, but it's about 2 to 2-ish solar masses.
Okay. So it's not the Chandrasekhar limit, but it's
A related limit.
Chandrasekhar limits says that anything beyond this cannot form a
White
dwarf. So it's going to go supernova sometime.
So in the core of a star, if it forms a core more massive than 1.4 solar masses, then it will inevitably cause a supernova and form a neutron star.
Okay.
And but these neutron stars also have a limit, and a star more massive than a certain size, these neutron stars are also not stable and they collapse into a black hole.
Wow. So every really massive star is a potential black hole.
Yeah, if they're very massive, more massive than tens of solar masses, they'll form a black hole.
Tens of solar masses, you mean 10 times more massive than our sun?
Yep.
Okay.
Otherwise, they end up as neutron stars, and both these scenarios involve supernovae potentially. But anything lesser than 1.4 solar masses will form a white dwarf.
Okay.
Which is what our sun will also end up doing.
The white dwarfs are by this deduction, we should have white dwarfs all around the universe.
Yep. We see white dwarfs all around the galaxy. These are hard to find because they're so dim and small. But we have found many of them, and many of them exist in binary orbits with normal stars. So we have found white dwarfs across the galaxy.
Okay. So this is one of the courses that you took. And
Yeah.
or rather, star was the formation of stars was one of the courses that you took.
Yeah.
So you're taking these courses in your first 2 years. And then what happens in a PhD?
So while at OSU, while taking these courses, you also start doing research projects. And after 2 years, you sort of formally get into doing just research.
Okay.
That's when you do something called your candidacy exam, where you have to present what research you've done so far. You get asked some questions. There's like an oral exam. You present a written research paper on some topic. And then you eventually start working on your PhD thesis.
Okay. So your PhD thesis is the work or the research that you are doing, which is probably not done before, or can it be done before?
No, so this has to be original research. And during a PhD, you're expected to write and publish research papers, which publish research papers in journals.
Okay. So now you're in that phase where you're actually doing research.
Yep.
And like you had mentioned, you're researching on gravitational lensing.
Right. So I'm doing research in an intersection of gravitational lensing and exoplanets.
Okay.
So I worked in gravitational lensing before, and I found exoplanets to be an exciting field for reasons we discussed before.
Yeah.
And I was lucky enough to find my advisor who worked at an intersection of these fields.
Okay.
So I'm working on a technique called microlensing, which uses this phenomenon of gravitational lensing to discover exoplanets.
Wait. So you're marrying your love for exoplanets or the excitement of finding exoplanets with the field you already worked in?
Yep.
And then now it's called microlensing?
Well, that field existed before.
Okay.
But yeah, I was lucky enough to find an advisor who works in that field.
Okay.
And I could get into it.
So explain this to all of us. It sounds fascinating.
Right. So we discussed how Einstein's theory predicts that light is deflected by a massive object like a star, and how Eddington observed, light from a distant star bent by our sun. So this can happen between any two stars in our galaxy.
Okay.
So if you're observing a star closer to us in the foreground, and there's a star in the background, which aligns perfectly with the star in the foreground, light from this star is bent around the foreground star before reaching us.
Okay.
And, we talked about how lensing produces multiple images before, but because these are stars and not galaxies and quasars, these images are not resolved. We can't actually see them.
Okay.
But what we do see is another consequence of lensing, which is the magnification of light from the background star.
Okay. So the light and the star in the background appears to be much larger?
Appears to be brighter and larger, but we can't actually see that. But it appears to be brighter.
Okay.
So when you monitor the light from this background star, if there is a foreground star that actually passes in front of it between us and the background star, the light from this
point of intersection, the background star
appears brighter. Yeah. So if you monitor how bright the star is for a long time, and you happen, so this is again a rare event because you need perfect alignment between two stars which are very far away, right?
And you have background data before the alignment happens.
Yeah. So you're monitoring these fields of stars constantly, and every now and then if you observe one star, you'll see that there's another foreground star that passes close to it, and the light from this background star it sort of increases temporarily, and then it decreases again
after the aligning star passes.
Because these stars are again moving relative to each other, and so this event lasts about a month or two. So it's time scale of months, and so you see this temporary increase in magnification and decrease. And so this is called a microlensing event. So this is how we observe gravitational lensing in stars.
Okay, you are looking into a field of the night sky. So you're probably looking at stars at different galaxies across the sky.
We can only completely resolve stars in our galaxy. Okay. So all of this happens within our galaxy.
Oh, so you're looking only within our galaxy?
Yeah, because other galaxies outside are too distant to observe individual stars.
Okay.
And we need to observe individual stars to see this microlensing event.
Okay, so you're looking at microlensing in the Milky Way.
In the Milky Way, yes. But we're looking at stars at various distances.
So how precise should be your the technology that you use to observe, say telescopes?
Yeah.
Your if I'm not mistaken, you mentioned that you're using IR telescopes right now.
That's right. So, as I mentioned before, microlensing is a rare phenomenon, right? It's a rare alignment, chance alignment of stars. So, if you want to observe many of these microlensing events, you need to look at regions of the sky where there are lots of stars
Okay.
to increase the chance of observing one such event. And the region with the highest density of stars in a galaxy is the center of the galaxy. But this region is very crowded. It has millions of stars very close to each other. So you need technology to be able to resolve these stars individually, to be able to see them separately. You also need IR telescopes to be able to look through the clouds of gas and dust that we mentioned before, that is there in the Milky Way, and peer through that to be able to see these stars.
Wow.
And you need to observe a lot of them very frequently. So
how many satellites do you actually require for all of these?
Well, right now, until now, this microlensing has only been done by ground-based telescopes.
Okay.
And because you need to observe these, monitor them constantly, because a microlensing event can happen anytime. These telescopes are spread across the globe, so that you don't have to wait for nightfall in one place to observe them.
Okay, so you're telling me that it's a network with all these telescopes where they look at the same section of the sky across different times?
Yep.
Okay, fantastic.
So these are...
It's a very globally collaborative effort.
A lot of astronomy is now done through global collaborations.
What?
So,
Okay.
but for the first time in about a year or so, we'll have the first space-based telescope that can do microlensing. And this is important because, as I mentioned before, you need to be able to observe these individual stars in these very crowded fields. Now, observing from the ground, you have the atmosphere between you and the sky, and this blurs stuff out.
And you have a rotating...
And you have a rotating Earth, and you can't observe it very frequently. You can't continuously stare at the same patch of sky, right? So, so this was what necessitated a space-based telescope to do microlensing, and that too, you can't do infrared astronomy from the ground because the gas in the atmosphere
will interfere.
They absorb infrared. So you need to go to space, and looking in the infrared will allow us to look at the galactic bulge, which is this very dense region with so many stars. And all these stars can act as background sources for microlensing events, like along the line of sight from us to the center of the galaxy. So this required a space telescope, and this was proposed, again, about a decade or two ago. And so this telescope has been in development for a long time, and it's finally going to be launched in a year or so. It's called the Nancy Grace Roman Space Telescope.
Wait a day. It's called the Nancy Grace
Roman Space Telescope.
Okay.
Nancy Grace Roman was a NASA astronomer who worked on a lot of things, including Hubble. So she's credited to be one of the key persons behind building the Hubble Space Telescope, which was the first space telescope.
Yeah, and now she has a telescope on her
to her name.
Wow.
So this telescope is, one of its main science objectives is to do microlensing. And it's going to observe the galactic bulge. It has a very wide...
galactic bulge.
The center of the galaxy.
Of the galaxy.
Yes. It's going to observe the center of the galaxy for a very long time, repeatedly observing the same patches of the sky to try and see if there are microlensing events. And as I mentioned again, you need to observe large patches of sky at once to get as many stars as possible. So the Roman Space Telescope has an aperture or field of view that's 100 times that of the Hubble Space Telescope.
100 times?
100 times. And even larger than that of JWST. So So it has a massive field of view, and it looks in the IR, and it has exquisite resolution. And it's able to measure the brightness of stars very precisely.
Okay, so give us a ballpark figure or an analogy to understand. How precise is this?
So these stars are separated by a few arc seconds.
Okay.
Now, an arc second, so this is a sector of a degree. So a degree has
60
arc minutes.
Yeah.
And each arc minute has 60 arc seconds. So this is
1/60th of 1/60th of a degree.
Yes, of a radian, which is related to a degree. So this is a very tiny distance,
Okay.
and we need to be able to resolve these stars to these tiny distances.
Hmm.
The Nancy Grace Roman Space Telescope is specifically designed to conduct this microlensing survey, look at the center of the galaxy, and try to see how many microlensing events we can find and how many planets we can find. Now, I don't think we got into how to find planets with this effect of microlensing.
Yeah, but it's getting fascinating with the telescopes and the yeah. So you were saying that okay, this micro lensing. Yeah. Now the funny thing is, everything is so far away and so precise. How on earth are you going to find planets between one star lensing another star?
Right. So this is the cool part of it. So as we talked about transits, where we are trying to look for these small dips when a planet passes in front of the star, but this requires us to monitor the light from the star very precisely. Microlensing doesn't need us to look at the light from the host star at all.
Okay.
So because gravitational lensing is a gravitational phenomena, if the star which acts as a lens has a planet around it, this causes a slight change to the gravitational field, a small perturbation.
Okay.
And so even the microlensing light curve, which you mentioned, the temporary magnification and the decrease in brightness of a background star when it's being lensed, this curve, this temporary increase and decrease in magnification, is also changed slightly by the presence of a planet.
Wait a second. So let me understand this. So the foreground star, which is between the observatory here, the telescope, and the observed lensed star.
Yep.
All right. So say for example, I'm sitting here. I am observing. So this is the star which is creating the lensing,
Mhm.
and then there's a star out here. Now, first I will look at this star, or rather, wait for an event for
Yep.
this star to lens something.
Yep.
And the background.
Yep.
And then I will start measuring the mass of this star.
That's right. So you can measure how much mass is there in the lens, and in a microlensing event where there's a planet, and the planet sort of perturbs this event and produces like a sharp increase in magnification or a decrease in magnification. And so, you have a smooth curve, but then there's a sharp increase or decrease.
Yeah.
And so these perturbations and these changes can be used to tell where the exoplanet is, how massive it is.
Wow.
So this is basically, it is definitely less intuitive than the transit method, but it is a very powerful method. And
So instead of getting a clean curve, you get a curve
bumps.
with one bump or a couple of bumps.
Yeah, and these bumps can be really tiny, and that's one of the advantages of the Roman Space Telescope is you can resolve these bumps more finely and look at even smaller and smaller bumps to find lighter and lighter planets, less massive planets.
Wow. And you're working on this?
Yeah, that's the technique I'm working on. And so the advantage of this technique over other techniques that we've used so far is related to something we discussed while discussing transits, that because of the observational bias, we can only see planets very close to the star and very massive. And this is true with other techniques as well. We can only see very massive planets. So there's this whole
Massive stars.
massive planets around stars. So
Massive exoplanets.
Yes.
So this is the one you explained where they're super Jupiters close to us. So that's the observational bias.
That's the observational bias with transits.
That is what you're trying to correct with your work?
That's right. So that's why this technique is useful, because it doesn't rely on, detecting light being blocked by the planet or something like that, where the size of the planet is important. So this just depends on the gravitational influence of the planet. So the planet can be much further away from the star.
Mm-hmm.
So until now, we've only been detecting planets in very close orbits. And so there's this entire range of space of orbits. We've not detected any planet like Jupiter in a Jupiter-like orbit around a sun-like star, because that orbit is too wide for transits to detect. And we've not detected any planet like the Earth, obviously. But this technique is more sensitive to planets which are actually further away from the star.
So in other words, you're saying that using these technique, we could find a Neptune.
Yep.
Or a planet as far away from Neptune to our sun.
Yeah.
In the observed planet.
Exactly. So it's more sensitive to planets like Neptune, like you mentioned. We expect to find, to be more
Still
than any about Neptune.
planet?
I think it's officially not a planet, but it's a matter of definition.
Okay. And what exactly changed? What definition changed for Pluto to be shunted out?
I think they just decided to draw a line. Definitely it's slightly arbitrary to draw a line between what is a dwarf planet and what is a planet. What is a rock versus what is a planet? What is an asteroid and what is a planet? So they're trying to make a distinction, and Pluto sadly fell on the other side of the line and was.
So what was it? Was it with the defined orbit,
Yeah.
or was it just the size of the planet?
I think both. I think planet is defined by its orbit, a stable orbit, as well as a certain size. And so yeah, those criteria were used to say that Pluto is not a planet.
Okay.
Yeah.
Okay. I had a friend who said that Disney character Pluto, people stopped watching, and that dog fell out of favor, so Pluto got kicked out. I don't know. But yeah, the arbitrary way in which Pluto got kicked out sounds pretty much like the thing. So, and you were also telling me that so this telescope is not yet gone out. It is still
It is completed being built. It's now sitting at the Goddard Space Flight Center in Maryland. And it's going to be launched late next year, if all things go well.
Okay.
Yeah.
So this was commissioned a decade and a half ago, or more
Yep.
than that?
Somewhere around that. Yep.
Wow.
Yeah. So it's gone through a roller coaster ride. It almost came close to being cancelled during the previous Trump administration.
Okay.
Its budget was set to zero, and then it was brought back by Biden. And again, NASA's facing some budget threats.
Oh yeah.
But yeah, I think it's going to get launched. People are pretty confused.
Existential threats.
Yes.
Years ago. Forget budgetary threats.
Yeah.
Okay. So so this is going to go out, and that's going to be probably in a couple of years, you say?
Yeah.
And that's when you're going to be a full-fledged PhD?
So yeah, that was like one of the selling points of this project that my advisor, what my advisor used to sell this project to me, that, you're going to be learning this technique, which is, again, fairly niche. And by the time this telescope launches and data starts coming in, you'll be well-versed in technique and you can start working on this.
Wow.
Yeah.
So this is slightly more than the 6 to 8 months you're used to.
Yeah.
But by the time your PhD comes through,
Yep.
I think the first satellite you're waiting for would also have been operational.
Yep.
Fantastic. So now you're in that period where you start writing papers.
Yeah. That's what I'm doing right now.
Okay.
Start writing papers.
So are you writing on microlensing right now?
Yeah. I'm working on a couple of papers on microlensing. One of the main projects that I'll work on through my PhD is to look at this class of planets called circumbinary planets.
Okay.
So these are planets that orbit not one star, but a pair of stars that are orbiting each other.
Wait. Now we are getting into two sunsets, two sunrises.
Yep.
Okay. Explain this.
So these are like, the planet Tatooine in Star Wars.
Yes.
So this was made popular where the Tatooine has two suns.
Correct.
For a long time, this was thought to be just science fiction. People thought it's not possible to have a planet around two stars. That system is too chaotic, and the planet
brings a three-body problem.
Yeah, three-body problem. It's not stable. But eventually, Kepler was actually the first telescope. The Kepler Space Telescope was the first one to find a planet in a circumbinary orbit.
Okay.
But again, as I mentioned, it uses a transit method, and therefore the constraint of the transit method is that it finds planets very close to the stars and in binaries with tight orbits very close to each other. And microlensing has the potential to discover more circumbinary planets and over wider ranges of parameter space. But the thing is, we haven't actually done a lot of work to see what a microlensing signal with two stars and one planet looks like.
Okay.
And we don't even know, how detectable they are, what kinds of planets will we detect, and how to detect them in the first place.
Okay. So that's like the untreaded path that you're going to go through.
Yeah. So I've been working on this for the past 2 years and continue working on it as.
So when you say I'm working on this, so you are you are actually trying to find planets around binary systems?
Yeah.
Wow.
Yeah.
Okay. So when you say you're working on that,
Hmm.
are you building simulations? Are you sitting and trying to see what kind of data will we get? How do we differentiate? So what do you mean by saying you're working on it?
Right. So what I mean is, right now the telescope has not gone up, so we don't have actual data, but we do know what the data will look like because we've seen these events, microlensing events before, and we have the theory for it. So I'm using the theory of microlensing, and I'm using computer code, some of which has been written before, some of which I'm writing myself, to create simulations which of circumbinary planets.
Okay.
So I'm creating what the microlensing event will look like, what the light curve, what this magnification event will look like when you have two stars and one planet.
Okay.
And so that's the first step, just to see what those events look like. And then the next step is how will we differentiate these from, one star and a planet, or
Okay.
just two stars? And how do we tell there's actually a planet around a circumbinary system? And the third part, what I'm working on, is to say how many such planets will we discover during the course of the Roman Space Telescope survey.
Okay. And how long is the survey?
The survey is going to last for the main part, the normal part of the survey is going to last for 5 years,
Okay.
but it could be extended if the telescope does well and it's in good working condition.
Okay. So help me understand this. So this telescope is not yet gone out.
Yeah.
But you are already making research data on what you might find as a feedback or as the input coming from
Right.
this.
So that's actually very important before the launch of a telescope, because we need to design how the survey is going to be. We need to decide where the telescope should point, how long it should look. And so these design choices are not arbitrary. They have to be driven by a scientific objective and a goal.
Okay.
So the first thing that people did was to establish what the goal is. We need to discover so many exoplanets, in these mass ranges, around these kinds of stars and so on. And then we need to design a survey, and we need to make sure that it meets these requirements. And
Okay. So when you mean you design a survey, you mean we are looking into this part of space,
Yeah.
this long,
yes,
and this is where we have the highest possibility of achieving our goal.
that's exactly right.
Okay.
So that's what we need to design and optimize the survey, because the survey has a limited time window, there are limited resources, and there are a number of science goals you have to meet. So you need to optimize all of this. It's basically an optimization problem. And to do that, we need to produce a large amount of simulated data.
Okay.
To be able to run our detection pipelines to even create detection pipelines and test them,
Okay.
and to decide whether we'll be meeting our goals with this survey design and so on.
Wow. So setting up a telescope is not just somebody just putting together the parts of it and sending it up.
Yeah. So there's a whole team of people working on validating the science goals, requirements, creating simulations, creating pipelines to analyze this data. Because if those pipelines don't exist when the data starts coming in, then the data is useless.
But this also puts me... All right, I was just looking at the timelines. Now, let's say this was commissioned 15 years ago. Arjun didn't know he's going to be an astrophysicist 15 years ago.
Yeah.
Yeah, probably you knew that that's what you wanted to do, but you didn't know you'd be an astrophysicist.
Mm-hmm.
And then now you're sitting and working on this, ready to get your PhD the moment it gets launched.
Yeah.
So you said a lot of teams. I think it's multiple generations working.
That's true. Yeah. A lot of people.
A lot of teams across different generations are working.
That's true. I mean, for someone like my advisor, who is right now heading one of these teams to, finalize the design of the survey and create all this infrastructure to analyze data, he's sort of been with this project since its conception.
Okay.
And, this project has spanned, it spanned his entire professional career, and he's sort of seen it, he sort of advocated for it when it was first, being decided.
Okay.
And then seen it through its design phase, conceptualization, and then finally now we have people, creating the final pipelines, the final survey design.
Which is students of his like you.
Yeah.
And when the data starts coming, you are going to be the professor who's going to be looking at it, analyzing it, and giving the results out.
Yeah, hopefully. That's
okay. So that truly, I mean, if you're talking about life cycles of stars, but a life cycle of an observatory itself, is huge.
Yeah.
Wow, that's something I did not know.
Yep. These are gigantic, multi-generational projects sometimes.
Wow, that's fantastic. And so we were talking about quite a few things, and we have almost come to a situation where we are only looking at what you're going to be doing in the future. Then, just for my curiosity, and I hope the audience is curious about this as well, I just initially brought up that, the composition of the universe, and you were telling me that the maximum 75% of the universe is dark energy.
Mhm.
We briefly touched on dark matter. This matter we don't see, but then we can observe through other or secondary observations,
That's true.
and then come to a deduction that there is a scene.
Mhm.
How on earth did we get that the maximum, most of the universe contains is dark energy? How did that happen?
So this happened through a number of observations. I think the first observation
Is a blue shift?
is the lead up to this is when Hubble discovered that galaxies are actually receding from us.
Okay.
They're moving away from us, and this led to the hypothesis of a Big Bang, that everything actually, if you trace back this, galaxies
fact,
receding from us,
It comes to a point.
it comes to a point, and it seems like they're receding from us in every direction, and so the jump in thought was that no matter where you are in the universe is expanding for you, because we're not in a special place in the universe.
Okay, yeah.
So
Because we are an obscure star at
Yeah.
the edge of the galaxy.
So that sort of set the stage for an expanding universe. But recently, late 20th century-ish, people, when they started measuring these recessional velocities with more and more precision, they found that the universe is not just expanding, but it's actually accelerating.
Okay, so it's going faster.
Yeah, and that is counterintuitive, because if gravity was the only force operating on large scales, then once the Big Bang has happened, gravity should be pulling everything together and slowing down the expansion. But it's actually accelerating. It's not just going at constant speed, but it's accelerating. So that was very counterintuitive, and that led to the proposition of this mysterious force called dark energy, which is supposed to counteract gravity and have a sort of negative pressure to push things away from each other.
Mhm.
And the leading theory for dark energy right now is that it's an energy associated with vacuum itself.
Okay.
So vacuum itself has a sort of weird property of, negative pressure, where it pushes things apart. And as the universe expands, it creates more vacuum and therefore creates more dark energy, and things start moving faster and faster, thereby accelerating.
Reason for the acceleration.
Yep.
So we're talking about vacuum energy.
A vacuum energy, yep.
Okay.
And this is
Is this classical energy, or is this
so we're not sure what kind of energy this is. It could be quantum mechanical. So that is the big mystery. What is dark energy at all? But we know how it behaves, or at least we think. Even that we're not entirely sure. And it is in the lambda CDM model. It is denoted by lambda, which was Einstein's cosmological constant, but now repurposed to be.
Are you aware of the history where Einstein said it was his biggest mistake, and then it finally, all those generations later, it comes back?
It does, yeah. So I think Einstein introduced the cosmological constant because his equations actually predicted an expanding universe, a not static universe.
And he said
the universe has to be static, because that he had a mental picture of what the universe should be, and he allowed his personal bias to come into his thinking, and he introduced this constant to stop the universe from expanding. But Edwin Hubble then discovered the universe is actually expanding, and Einstein scrapped this. But the constant has been reintroduced in another form, where it's actually accelerating the universe. And it is an energy associated with vacuum, which is, causing this acceleration.
Wait, did Einstein not leave it there and just lament about adding the constant?
He eventually took it down. He said it was his biggest blunder of his life.
Okay.
And that once Hubble's experimental results came out, there was no doubt that the universe is expanding.
Wow.
Yeah.
So a blunder now comes back.
Yeah. Full circle. And but I mean, the exciting thing is that the nature of dark energy and whether or not it's a cosmological constant itself is being brought back into question again, because this was cosmological constant is supposed to be a sort of constant energy associated with
Exactly. But
vacuum.
then this is an accelerating.
The constant energy does produce acceleration, but so recent experiments have found that, or at least are beginning to find signs that maybe this dark energy is not a constant at all. Maybe it has changed over time. And so this is all still very speculative.
There's a function of time with the.
There might be. And so this is, again, I'm going to put in a shameless plug for Ohio State. So Ohio State is part of this collaboration called the Dark Energy Spectroscopic Instrument.
Okay. Dark energy spectroscopic instrument.
So it's a telescope, a collaboration, which set out with an ambitious goal to measure the positions and spectra and redshifts of millions of galaxies.
Okay.
And so far, it has measured about 30 or 40 million galaxies to create this map of how galaxies are distributed in the universe, how they cluster across time and space.
Okay.
And so until now, we have been able to measure the expansion or acceleration of the universe using, more local indicators in the local universe, things closer to us,
Yeah. So,
and on smaller scale.
okay.
But we wanted to see what happens if this theory holds, if the cosmological constant theory holds even on very large scales and across different time scales.
Okay.
And so this experiment has created this huge map of millions of galaxies. And the first results of this experiment came out, again, a couple of months ago. And this was just the first data release, so it's still very preliminary. We can't make many conclusions out of this. But the first preliminary results showed that perhaps what we thought dark energy was is not what it is.
Okay. And why is that?
So their results found that this expansion of the universe is not consistent with a constant dark energy, but a dark energy that's actually evolving with time. And so this acceleration might have been faster or slower in the past and might actually change in the future. Okay. So till now, the rate of acceleration is constant. Okay. It's accelerating, but at a constant rate. But that's why the cosmological constant. But these experiments are showing signs of, this
a varying strength through the
varying dark energy.
Okay.
But even this is just sort of trying to get at how dark energy behaves, but we still have no idea what actually it is.
So a rudimentary thought comes into an untrained head. We have the cosmic microwave background, which actually predicts the varying density. So pretty much where galaxies are in the background.
Yeah.
When you project from that.
Yeah.
Is that how this was structured?
That is very close to how DESI, the experiment, sort of calculated the expansion history of the universe. So the cosmic microwave background is a relic of the Big Bang. So when the universe started out as, a very hot, dense point and then expanded, for a long time, it was just filled with electrons and protons and radiation. And this was all these electrons and protons, which were ionized, were just, constantly absorbing and scattering light. So this was an opaque ball of, opaque universe. And with time, when the universe expanded and cooled, these electrons and protons combined to form hydrogen nuclei, and the universe suddenly became transparent. And photons, which were trapped until then because of this constant bouncing around between electrons and protons,
started
to stream freely. And this radiation from that era, redshifted, sort of, stretched in wavelength, is what we observe all around us as the microwave background. Now, at this era, there are some processes which left some physical imprints in the microwave background, which also later on translated into imprints in the galaxy distribution function.
So basically, what to make it simpler, the universe was almost homogeneous, as in all directions, the density was pretty much the same, but there were micro variations here and there. Now, as the universe expanded or evolved from there, all these places where there was micro greater density, they started coalescing together, and that's what formed galaxies.
That's right. So those over densities formed the structure that we see today. And using our understanding of physics of the early universe and our understanding of physics in general, we can sort of predict how those inhomogeneities and those fluctuations should have been. And if we start from known fluctuations and we use our theory of cosmology and how the universe expanded, we should be able to tell how galaxies are distributed in the universe today.
Correct.
And so if we measure how galaxies are actually distributed and then correlate with what we observed with our known knowledge of inflation and early universe, we can test if our understanding of cosmology is correct. And so this is basically vaguely the concept that they used in this experiment to measure the distribution of galaxies and our knowledge of how the universe expanded to try and see if what we thought is actually true and the galaxies actually distribute that way. And this led to some surprising findings.
Okay, so there is some evolution with energy over the time span.
There might be. It's a very big if and might.
Okay.
But yeah, more results over the next few years will probably give us a better picture. But this is to say that it's still a constantly evolving subject, and these are like some of the biggest questions.
Okay. So now that you're well within the well on to get your PhD, and I'm pretty sure you're going to get it pretty soon. What is exciting in astronomy or astrophysics for you right now? And if you would want to explain what is exciting you right now from within the industry to the kid who is reading the popular science magazines, how would you do it?
Well, I think we went through a lot of this before, but there's a lot of excitement in almost every field in astronomy right now. So even so within exoplanets, the very fact that exoplanets exist is itself very exciting. There's the prospect that in the next decade or so, we might discover life on one of these planets.
Okay, the Holy Grail.
Yeah. The Nancy Grace Roman Space Telescope is going to discover 1,000 to 1,500 exoplanets, new exoplanets. And this will sort of complete our statistical census survey of planets in our galaxy. We would have discovered all possible types of exoplanets, or so we think. We might, be in for some new surprises.
Okay.
So that's like a thing that's going to happen very soon, and it's very exciting. There's excitement in cosmology, like I mentioned. We're we're discovering new things about dark energy and dark matter. The most exciting astronomy, there are like so many new facilities and telescopes being built today that the pace at which these new observatories and facilities are being built and commissioned is much faster than it has ever been in the past.
Okay.
So this is possibly the most exciting astronomy has ever been, and could be a golden age for astronomy.
Okay.
So to give you some examples, the James Webb Space Telescope launched a few years ago.
Correct.
The Nancy Grace Roman Space Telescope, a sort of successor, will be launching soon. The European Space Agency has launched a telescope called Euclid, which is supposed to answer questions about dark matter and dark energy.
Okay, so that telescope is launched with experiments geared to
answer questions about dark matter. Yeah.
Okay.
Many ground-based telescopes are being built. So there are these class of telescopes called the extremely large telescopes, or 30-meter telescope.
Okay.
These are the biggest telescopes mankind has ever built. They have a telescope mirror which is 30 meters in diameter.
Wow, 30 meters?
30 meters. So
my goodness.
These are way bigger than anything we've ever built, and they're going to be on the ground, and there are 2 or 3 facilities that have been planned, some of which are already under construction and very close to, pretty advanced in the construction phase. And these will be commissioned in the next decade.
Okay.
And when these come online, we'll have like a whole new way to look at the universe with an instrument which we have never, ever used before.
So this is like somebody using a Motorola feature phone suddenly getting exposed to Apple 17 Max Pro.
Yep, something like that. Well, I mean, we've definitely used telescopes between those two as well, but this is definitely a huge, step up in a large sense. There was a new telescope which just started operating a few weeks ago, called the Vera Rubin Observatory.
Yes, I've heard of this.
Yeah, and so this telescope has the largest digital camera ever made installed in it.
Yep.
This is about 3 gigapixels,
3,000
megapixels. We have 50 megapixel cameras on our phones. This is 3,000 megapixels, and this camera is going to survey the entire night sky once every few days.
The entire night.
The entire night sky. It's going to operate robotically, remotely. It's going to automatically conduct a survey, image the entire night sky every few days to look for transient phenomena that happen over the time scale of days.
Okay.
Supernova explosions, black holes accreting, neutron stars merging.
It's going to do all that.
It'll be capable.
Wow. That's why it is 3,000 megapixels.
Yep. So it's going to have a huge field of view, so it can cover the night sky very quickly with very high resolution, and it's going to be used to do a wide variety of science. So there have been a large number of facilities which have been coming online and doing a variety of science.
Okay.
Very recently, we discovered and detected the first gravitational waves, which is like a whole new window to the universe.
Wait a second. Explain gravitational wave, because I think the audience is going to be extremely
right. So in brief, these are again a prediction made by Einstein's theory of relativity. So massive objects curve space and bend the fabric of space. When these objects are really massive, like black holes and neutron stars, and they're moving really fast, they produce ripples in space-time, and these ripples can propagate outwards like waves. And this was only theoretical, and it was sort of a theoretical concept. No one thought we could actually detect these waves, because these produce very small observational signatures. So what these waves do is, since they're waves in space, they sort of very slightly stretch and squeeze space, and stretch and squeeze matter and change length scales very slightly. And so these are changes when they reach Earth. These changes happen on a scale that is smaller than the extent of a proton.
Okay.
So we've built detectors at these LIGO detectors in Livingston and Hanford in the US. There's one in Europe, and there's one LIGO detector being built here in India.
So explain to us what a LIGO detector is.
So LIGO stands for the Laser Interferometric Gravitational Wave Observatory.
Right. And these are the ones that are way down in mines?
Nope. These are detectors on the surface. So these are all LIGO detectors consist of 2 4-kilometer long tubes.
Okay.
These are concrete tubes. They're built at right angles to each other.
Okay.
Through these 4-kilometer tubes are completely all air is sucked out of them, and they're completely made into perfect vacuum. Yeah.
Okay.
So you need very strong vacuums inside them. You need very low densities, and you shoot very powerful lasers from these two ends.
Okay.
And these lasers bounce off very well polished and precisely measured mirrors, or just suspended. So when a gravitational wave passes through the Earth, because of the nature of gravitational waves, it sort of stretches and squeezes space in different extents along the two different tubes.
And so you're measuring the speed of the reflection too.
We're measuring, so these two laser beams are combined to form what is called an interference pattern.
Correct.
And this interference pattern depends on how long these two tubes are, how much time light takes to travel in these tubes. And when gravitational waves change the length of these tubes differently, it changes this interference pattern.
Oh,
and this requires us to measure, the position of the mirrors to less than a width of a proton. So this is like extremely precise.
Less than the width of a proton.
That's true.
Which is next to nothing.
Yeah, that seems nearly impossible, which is why it took so long to build, and it was considered a nearly impossible dream, where it actually happened. And now we've detected gravitational waves from tens of massive black holes merging together, which we had never seen before, but we knew could happen, and now we see that they do happen.
Wow.
We've detected gravitational waves from neutron stars merging together.
Neutron stars merging together.
Yep, 2 neutron stars orbiting each other and then merging.
And so the ripple effect of that which has probably happened a billion years ago.
Yeah.
You are actually observing that in the LIGO detectors?
Yes.
Wow.
So, there are more LIGO detectors being built. There'll be one in India in some time. They've gotten the full green flag go ahead to start building India's own LIGO
Where is
detector.
that going to be?
It's going to be in Maharashtra.
Okay.
Actually, fairly close to Pune, I think, where they've got a site to build, these 2 gigantic 4-kilometer vacuum tubes,
Okay.
and with lasers shooting through them to measure these tiny ripples in space-time. So that's something that'll be very exciting. And this field is only evolving and detecting newer and newer kinds of events, changing our understanding of how black holes evolved, what neutron stars are made up of, and answering questions like this. So there's that. And, in every other field where I mentioned before that James Webb has been able to look at the birth of stars and the birth of planets.
Correct.
So we're learning about how planets form in these disks. We're learning about what happens when a star dies, about a supernova. So even though I sort of painted a picture of what happens in a supernova, a lot of details in this are missing. We don't know a lot about what actually happens in those moments when a star collapses
and then bounces off into
Yeah.
supernova.
So there are a lot of people working on this. And then, there could be a new field that is, because all these are very cutting edge telescopes. And when they actually start operating, you don't know what they'll discover next. And so
You don't know what you've not been looking for.
Exactly. So I think this is definitely a very exciting time to be in astronomy and astrophysics.
Wow. Arjun, it's been completely fascinating to actually hear about what is happening, what your journey has been through, and the kind of things astrophysics, astronomy, or cosmology holds for us. Extremely excited to see what you bring forward. And the next time you're back in India, so you're in Ohio State, like we found out, and you're here just on a holiday.
That's right. Yeah, I'm here for a short break. Yeah.
Okay. So I think it is pretty prophetic. And then I think we're going to have another one a few years down the line
Sure. Yeah.
where you can let us know what are the new things that are happening.
I'll update you on the progress after a few years. Yep. Thank you for having me. This has been a really great conversation.
Thank you so much, Arjun, for being on Conversations in Bangalore. The pleasure is all ours. And like I said, it was foretold that you are going to be here. You were here, and what a conversation we have had. Thank you so much. Look forward to catching up with you, and all the best for everything you're pursuing right now. And let's keep in touch through if needed, we will connect. And please promise us one thing, that if there is something exciting happening, you will let the viewers of Conversations in Bangalore.
Yep, definitely. I will update you as soon as the next most exciting thing happens.
All right. Thank you so much again.
Thank you.